Hello everyone, hope you are doing great. So in the last class we learned about the symmetry elements and symmetry operations. We learned how to find out the symmetry elements and symmetry operations also, and then toward the end we said that after learning this whole set of symmetry elements and knowing how to find them out, we need to utilize some sort of mathematical framework to so that we are able to employ these symmetry elements belonging to a particular molecule in order to get some molecular properties out of it. So in other words, we need to learn about the applicability of this symmetry aspect of molecule, and in order to have these applications we need a quantitative framework, a mathematical framework which is known as group theory. So in this particular theory, which is purely a mathematical framework by its origin, so long before chemists started using it, mathematician started this particular beautiful topic called group theory. So all these symmetry elements can be utilized to form a particular group. We'll come to those things in a while. Now before we can form a so-called group or something, and based on the symmetry elements of a given molecule and utilize them to find out various things like how to form a linear combination of atomic orbitals, or how to find out the probability of transition between two molecular electronic or vibrational states. Before we do that, we need to learn a few basic things about this group theory. So a few criteria of something that can be called a group. So let's start with the definition of this particular thing called group. So what is a group? So a group is a collection of objects, or it's a set of some distinct object. So if I can say is a set of some elements, okay. So a set of elements can form a group. Now I hope all of you understand what is set. Set is nothing but a collection of some distinct objects, okay. Suppose I take a few numbers, say like 1, 2 and 3 together, it will form a set. So 1, 2, 3, these three numbers, they are distinct objects, right? When I put them in a collection, they form a set. So here we are considering such a set, and this set can have any type of elements, okay. It can be some numbers, it can be some different objects, anything, and the number of elements of any set can be anything starting from 1 to infinite. So if I take any particular set having certain elements in it, and then if there is a particular rule of combination, okay. So what I need, number 1 is a set of elements, number 2 a well defined rule of combination, okay. So rule of combination, that can be anything. Suppose I told you about a set like 1, 2, 3 and so if I tell that okay, the algebraic addition is a rule of combination which can actually combine any two elements of the set. So I have a set of elements and I have a particular rule of combination which is well defined in this. Then I can have a group. This set will be called a group provided certain rules are satisfied. Okay. So what I have now, I have a set of elements and a particular definition of rule, a particular rule of combination is defined in it. It will be called a group once it follows certain rules. So what are those rules? So those rules are as follows. So there are 4 rules or 4 laws. Okay. So rule 1 says that all the elements in a particular set, if I consider them, and if I take any two from any two element from that pool of elements and then combine them with that defined combination combination tool, then the product, or if I say that the effect of that combination, okay, this product may not necessarily mean the mathematical so called product, but if I say that the product and combination is synonymous, so you can take it in that way. So the product of any two elements, so suppose I have a set which is formed by some element like A, B, C and so on, okay, up to say so x. So there are x number of elements in that particular set, and there is a particular method of combination. Okay, so this is the method of combination, say, is defined in it. Then what this rule says, that product of any two elements, say A and B, both belongs to the set A, right? So A and B, they belongs to set S. Then the result of this combination of A and B, suppose that produces something called say M. Okay, so then this law says this M must be an element of set S. Okay. Similarly, I can say that I don't have to multiply only two different elements. I can have something like this. I can have the product of A with A. Okay. So in other words, the square of any given element, say if that is n, then n should also belong to S, and here M should belongs to S. Then I will call this set as closed set. Okay. So when this is satisfied, so if this rule is satisfied, we will call this set as closed. Okay. And this particular property is also known as closure property. So the first rule for a set that can be called a group. So in order to call a set a group, this first rule must be obeyed. If it fails, if any set fails to satisfy this condition or this property, then it will not form a group. Okay. So the first one is the closure property. So let's write down all of them one by one over here. So in order to form a group, it must satisfy closure property. Number 1. Okay. Now I said there are 4 such conditions. If they are met, then they will make this set a group. And we learned about the first property, that is the closure property. Now, which one is the number 2? So, number 2 says that there must be an element within this set. Let us consider this set again. So, it says the law 2 says that there must be an element in this particular set such that it commutes with any of the elements. So, mathematically, if I try to say this one, it will be that there must be an element E belonging to this group S such that E commutes with any element of this group, of this set. This is not yet group, right? So, E, if I operate on any element here. So, if I operate, so we have this as my defined operation, which is also a binary operation because it combines 2 elements. Okay. So, I have E star, say A. Now, A is an element of this group. I can take any such element. Then it should be same as A star E, which is nothing but equal to A, right. So, it says that E commutes with A. Commit means it does not matter the order of combination, so whether it is E star A or A star E. Okay. Here the only difference is the order of combination, right. So, the order of combination does not matter and it ends up giving back the element itself. This element E is known as identity element in that particular set. So, you can correlate between this identity element and the identity element that we talked about when we discussed the symmetry elements. Okay. So, you can see they are exactly the same. So, according to rule 2, we have that there must be an identity element defined in that group, right. So, whatever we said so far, we can say in a single sentence that we need an identity element to be present in the set. Then only I can call this as a group. Okay. So, this is called, that means I need an existence of unique identity element. Okay. So, you cannot have 2 such elements in a set and still it is a group. Okay. So, there will be only one element of its kind. Okay. So, that is why it is unique, and this element is known as identity element. So, we have found 2 conditions for satisfying that needs to be satisfied in order to form a group. So, let us move on to law 3, which says that the law of associativity must hold for that particular set in order to be called a group. So, it says law of associativity must hold. What does that mean? We know what associativity means, right? Associativity means the order of combination. Okay, suppose I again consider this particular set having A, B, C to X. Then if I take out 3 elements from that, okay, so I consider A, B and C, these 3 elements I take and then combine them in an order like A, in this way. Now if I change this order of combination in such a way that let us not put this equality now. Now this and this, what is the difference? The difference is here, this bracket is making all the difference. It says that first I will combine B and C and the resultant will be combined to A. On the other side, here I combine A and B first, and with this result I combine with C. Now if the associativity holds, then these two should be equal. This is law of associativity, and in order to form a group, the set must satisfy this law of associativity for any element belonging to this particular set. Okay, so we got our third condition, that the set must have associative property, and then we must have another rule that has to be satisfied. Okay, so we come to the last rule, that is the law of reciprocation. Okay, law of reciprocal, or we can say law of reciprocation. What does it say? It says that for this particular set, if I choose any element, any one element, if I pick up, so arbitrarily I pick up say C, then there must be an unique reciprocal or inverse for this particular element. So I choose say C, C belongs to S, then there must be some element which will be reciprocal of C, which is written as C inverse, right, such that this combination will give me identity. So according to that law says that there must be some element here, say I call it like Q. So this C inverse and Q will be equal. So that means for any given element C belonging to S, I will find an element Q which will combine with C to give identity. Okay, and that is true for any element belonging to this set S. So if I take A, there must be some element there R that yields A star R equals to E. Okay, so the fourth law that we have here is the existence of unique inverse. Now again here we have this term unique, because in a set you can have only one inverse of that particular element that we are choosing. Okay. If I choose A, then there must be only one element, say R, such that R is equals to A inverse. Okay. And you will not find any other element which will be reciprocal of A again. Okay. So, this reciprocal or inverse of A must be 1, and that must be a part of this set. Okay. So, then I will say that this set has all the elements of the set has their own unique inverse. So, once I check all these properties, the rule 1 closure property, if it has an identity element in the set, if the elements of the set follows associative law, and if there is an unique inverse for each and every element of the set, then I can call this set as a group. Okay. So, this S will be a called group, and most of the time we give a symbol G, not necessary, but you will find out that mostly we use G because group starts with G, people use G to define a group. So, G, and then you write like a set. Now, let us revise what do we have so far. Any given set, okay, that is a collection of elements, will be called a group when a particular rule of combination is defined in it and all the elements follow certain rules. One, closure; second, existence of identity; third, law of associativity holds; and fourth is the existence of unique inverse. Then it will be called a group. If the elements of a set cannot satisfy even one of these conditions, it will not form a group. Okay. So, that has to be verified all the time whenever we are trying to find out if a set can form a group, if I define a rule of combination. Okay. Now, we have defined group. Now, at this point I will mention an additional point about a group. A group will definitely follow all these 4 rules. Okay, they will obey all these 4 rules. Now, if the elements of that set which follows all these rules and they have a well defined binary operation in that, additionally if it follows a rule, as I am going to show you, which is known as commutativity. So, additionally, if the elements which follows all these rules, if they follow rule of commutativity or rule of commutation, then if this hold, okay, if holds good, then obviously that will be group because they have already satisfied all the condition for being called a group. Now, additionally they are following this particular condition of commutativity, which means for any 2 element A and B belonging to a particular group, if A star B equals to B star A, that means A and B commutes, right. So, once this holds good for any element A and B belonging to G, then that particular group is called an abelian group. Okay. So, this is another very important type of group that we will come across. They have some unique properties and all. So, we have learned so far how to define a group, okay, and also we learned that there is a special kind of group which is known as Abelian group, where apart from all these 4 properties, an additional property of commutation also hold good. They are called abelian group. Now let us take some actual example, okay, and then try to find out if we really understand this topic, okay. So let us define a set. Let us define a set S which contains all the rational numbers, okay. So which is a set by rational numbers okay, that is possible, all right. And we defined say an algebraic multiplication, okay, as my rule of combination. Now is this set going to form a group under this binary operation which is multiplication? That is the question. Let us try out. So in the set of rational number I have everything, right. I have infinity here, I can have 1 upon infinity, okay. So all the numbers are there. So now I first check if there is a defined operation, that I already said yes. So okay, multiplication is my operation. Now first thing is the closure property. Now I take any 2 rational numbers, because I have all the rational numbers in my set. So I take 2 and 3 and then see if all these properties hold. So 2 and 3, if I combine, it will give me 6. 6 is also a rational number, so it belongs to this one. So I say closure property it is satisfied, okay. Now is there any identity element? It is very easy to find out, right. Identity element will not change that element with which it is being combined, right, and it will commute with that. So if I take any element, say I again take 3, can I have something, say can I have something, I am putting it under a quote, I am not writing what is it, such that I will have 3 into this equals to 3? Answer is very obvious, right. It has to be unity. So now check with any given number, you take it 5, 5000, anything, multiplication with 1 will return you the same number, right. So I have 1 as the identity element. So I found my identity element. Now does it obey associative law? Let us see again. So I have 2 into 3 here, right. So let us take 2 into 3 into 4. Now if I change the order, 2 into 3 into 4, obvious answer is these 2 are equal. So associativity holds good, okay. So associativity holds. Now we are left with the existence of unique inverse, okay. So what does an unique inverse do to any element belonging to a set? That inverse will combine with the element to produce identity. So let us take 3. So I have to combine with something which will produce my identity, which I already have got as unity, Okay, and similarly, if I this will be commuted, so the answer is obvious. I should have something like this. Okay, so I have for any given element such as 3, always I have 1 upon 3, and this combination, that is the multiplication of 3 and 1 upon 3, is going to give me unity, which is the identity element for this group. So this particular set of rational number is a group under binary operation multiplication. So this I can call it as a group under multiplication. Okay, so I will quickly give you another example, that is the set of, say, all integers. Okay. So the previous one was a group under multiplication. Okay. The next set I will take, say, all integers, both positive as well as negative integers, including 0. Okay. So including 0, and I define an operation as addition. Now quickly check if the set of all positive and negative integers including 0 will form a group under the binary operation addition. First, closure property. Take any two elements, again 2 and 3. 2 plus 3 equals to 5. 3 plus 2 is equal to 5. 5 is a positive integer which is already a member of this. You take 5,000, 10,000, combine them, you get 15,000. What is that? Is an integer, belongs to this particular set. So closure property holds for this particular set under binary operation addition. Now, is there any unique identity? There is one. You can see I have the set which has all the integers which includes 0 specifically. So if you add 0 to any number, it is going to return you the same number. So it will also commute with any number, right, under addition. So 0 plus 5 equals to 5 plus 0 equals to 5. That means 0 is an identity element in this particular set when I use addition as my binary operation. Let us look at the third one, associativity property. It holds good because I have, say, I have something like minus 2 plus 3 plus 5, and then I can write minus 2 plus 3 plus 5. Both of them are going to give me 6. So associative law holds. So third point is also clear for this set under addition. Existence of unique inverse. So inverse demands that for any given element I will have another element with which if I combine my previous element, it will result in having the identity element. So if I take, say, for example, any element, say, plus 2, do I have something with which if I add this plus 2, I will get my identity. What is my identity? I got my identity as 0. So plus 2 will be adding to something which will give 0, and that something must be minus 2. So if I take, say, another example like minus 15, so I have to add with plus 15 in order to get my identity element. Now all these numbers are integers, so I have unique inverse for each and every element with in this particular set which has unique inverse. So I have set, I found out that all the conditions, closure property, unique identity, associativity, as well as the existence of unique inverse are hold good, they hold good under the binary operation plus. So we can call that the set of all positive, negative integers including 0 forms a group under binary operation addition. So you should try many more such things. For example, if you remove this 0 from this set, try it out. Find out if it forms a group under addition. Does it form a group under multiplication? Or the first problem that we solved today, where we define multiplication as the binary operation, will it form a group under addition? So try out many such operations, and that will help you getting the basic essence of this mathematical group theory. So with this, we'll stop here, and we'll come back with a little bit more about the group theory, particularly how to combine different elements of a group using something called group multiplication table. That will be necessary to understand the combinations of different symmetry elements, which is our actual goal. So we will learn about group multiplication table, and then we'll move to the combination of symmetry operations. So with that, I come to the end of this class. Thank you very much for your attention, and see you next week.